Hello and welcome to another tutorial video from UniScience. In this video, I will explain you the setup of a 3D robot with LINAX linear motor stages and 3 LINAX servo controllers. A typical design for a 3D motion application consists of a LINAX LXS shuttle, which is the basis x-axis for long strokes. Over the x-axis, we find the LINAX Lxu universal, which is mounted directly back-to-back to the carriage slider of the LXS. At the one end of the y-axis, there is a Lxu front flange mounted to the front face. Attached to this front flange is a LINAX Lxc compact with weight compensation. The payload of 250 grams represents an application tool. The LINAX linear motor axes are connected to the LINAX servo controller. With the Ethernet switch, we combine 3 single-axis servo controllers to a multi-axis operation via TCP/IP by a computer. We provide the switch box with power, then we connect it with the company network and with the computer with which we control the axis. Then we connect the x-axis, the y-axis, and the z-axis. The logic supply is always 24 volt DC. The power supply voltage depends on the LINAX type and the requested speed. If you have a Lxc compact linear motor axis with only 10 Newton nominal force, then a 24 volt power supply with 5 ampere is sufficient. If you have a 24 volt power supply, you could use the same supply source as for the logic supply. In that case, you would need only one supply device. For a LINAX Lxc with 40 Newton or LXS and Lxu axis with high dynamics, a separate power supply of 48 volt with 5 to 10 ampere is needed. For long LXS axis with more than 500 mm stroke at speed up to 4 meters a second, a 72 volt power supply is recommended. We suggest to start the setup with the axis that has mounted the payload. First, we will adjust the optional weight compensation. As mentioned before, the weight compensation works with compressed air, but has no air consumption. With the commercial air pressure regulator, the compensation force can be adjusted. In case of power interruption, the carriage slider remains in position like you see now. Or it moves upwards to the mechanical limit depending on the air pressure regulator adjustment. If you have a long-term interruption and the compressed air isn't available, you could use a simple compressed air volume with a one-way valve as you can see in the graphic. The compressed air volume works as a reservoir. If a little air escapes through the gasket of the LINAX weight compensation, the compressed air volume refills continuously the cylinder of the weight compensation. The result is that the carriage slider remains in position over several days, even when the air pressure supply is turned off. Then we start with the electrical setup of the z-axis. First, we enter the corresponding IP address into the web browser. Note, if we just enter the IP address number without the start file name xanax.html, we can select Xanax afterwards. Then we are going directly into the operation menu. With the command line, we activate a reset to set all parameters of this LINAX Lxc85F10 to its default values. Next, we enter the payload value of this z-axis, which is 250 grams. This is the only parameter which you have to put in manually. Now we are ready to start the movement of the axis. As you know, it is important that the first command after switch on the power is the reference. The reference function calculates the absolute position of the axis and makes a fine adjustment of the electrical commutation angle in the linear motor. The absolute position from the reference remains active as long as the logic supply is active. If the motor power supply of the linear axis turns off, or if there is an axis error, you can restart the movement without activating the reference function. You can simply enter the ASCII command PWC or push the button power count for power continuous. To sum up, as long as logic supply is not interrupted, it's not necessary to run the reference function again. Then we move to the absolute position to 0 with go position 0. Then we adjust the soft limit position positive to the value of 70,000. With the standard measurement system of the LINAX linear motor axis, one increment is 1 micron. This means that the axis limits its stroke at the absolute position of 70 millimeters. For the test, we use the repeat reverse function and enter a distance value of 60,000 increments. Pressing enter brings the linear motor in motion. To better test the accuracy, we enter a weight reverse of 100 milliseconds. Now we check the accuracy and have a look at the motion diagram. With new record, then upload, we can see the position and speed diagram. We test the accuracy at the arriving position of 60,000 increments. We find an overshoot of 10 microns. To reduce this overshoot, we increase the stiffness of gain position to the value 80 in the navigation window state controller. Then we are testing the accuracy again by recording and uploading a new sample. The overshoot is now reduced to 3 microns. Then we save the z-axis parameters as application file.jsc to the computer. At the same time, Motion does also save a report file. Later, you can print out this setup report as integral part of the machine documentation. Now we go on to set up the y-axis in the same way as the z-axis. We enter the correct IP address, in this case with the ending 202. Then we click LINAX to start the Java applet. We wait for the system check to run. And reset the parameter of the y-axis to default values with the ASCII command res. Next, we have to calculate the payload value in the state controller navigation window. 250 gram for the payload of the z-axis, 650 gram weight of the z-axis, and 170 gram load of the weight compensation of the z-axis. This results in a total weight of 1070 grams. You can find the weight of each linear motor in grams on our website, for example under downloads in the Uni Science brochure. Each series has a chart where all models are listed with the weight of the carried slider and the total weight. As before, we first have to run the reference function. Then we go to the absolute position of 0. In order to test the accuracy, we enter a repeat reverse distance of 50 mm, which equals 50,000 increments, with a wait time of 100 milliseconds, and press Enter to start the linear motor axis. The wait time helps us to better view the accuracy in the motion diagram. Now we increase the dynamic with higher acceleration and higher speed. Then again we have a look at the motion diagram. The graphic shows an overshoot of 5 microns. That's already very precise, but we can try to improve it by increasing the stiffness in the state controller navigation menu. By the way, you can do this while the axis is running. We set the gain position from 50 up to 70 and test again. The result is a reduction of the overshoot by 2 microns. We stop the motion and save this y-axis parameters as application file to the computer. Lastly, we set up the x-axis. It is the basis axis which supports the y-axis, the z-axis, and the payload. We open a new web browser window and enter the IP address with the ending 201 and click LINAX. Then we proceed to operation. With the comment line, we activate the parameter reset with the comment res. In the menu state controller, we enter the payload, which consists of the following calculation. 250 gram for payload of the z-axis plus 650 gram weight of the z-axis plus 170 gram for the weight compensation on the z-axis plus 1900 gram for the y-axis. This equals to a total weight of 2970 gram. The next steps you know from the setup of the x and y-axes earlier. We run the reference and enter the repeat reverse motion with a wait time to test the accuracy. Looking at the motion diagram, we find that the overshoot is only 3 increments. That is great and very accurate, so we don't have to do an additional fine-tuning. Click the button Save and then to File to save this x-axis parameters to the computer. And now, as a final showdown, we will see all axes together in action. We start the z-axis with power continuous, then we go to position 0. By pressing Enter over the stored values, we set the axis in motion. We do the same with the y-axis and set the linear motor in motion according to the values entered before. In this example, it is a stroke of relative 60 mm. Last but not least, we set the x-axis in motion with the same steps. Note that for all 3 axes there is no need to run the reference. Now we increase the dynamics and the speed for the whole system by adjusting one axis after the other. By the way, the parameter scales do not reflect the maximum of the values. Behind in the empty panel or with the ASCII commands SP for speed or AC for acceleration, you can enter higher values manually. This is a nice demonstration to show you the potential of these compact and light linear motor axes. You can easily stop the motion of each axis with the corresponding stop motion button. Your 3D robot is now ready for the programming of your individual application. We wish you the best of success. Once more, you see how easy the setup of our products is. You're welcome to contact us for more information or if you have questions. Thank you for your attention.